So today I'd like to talk about a method for proving strong converse in network information theory, and also its application to parallel repetition theorem, which is an important problem in computer science and cryptography. So let me start with background. So in point-to-point channel coding problem, Shannon's coding theorem claims that the optimal coding rate for vanishing error probability is characterized by the capacity. So this theorem means that up to the capacity, the error probability can be 0. But above the capacity, if coding rate is above the capacity, the error probability cannot be 0. Usually, this kind of claim is called weak converse in information theory. On the other hand, the strong converse theorem, first proved by Wolfowitz, claims that if the coding rate is above the capacity, then the error probability must goes to 1 instead of 0. So this is a kind of sharp phase transition phenomenon, and it's very interesting theoretically. And also, it is an important stepping stone for finer asymptotic analysis, such as second order coding rate. Usually, proving strong converse, especially for multi-terminal problems, is very difficult, and we need some sophisticated techniques. For instance, Alswede-Gatch-Kellner introduced a technique called blowing up lemma to prove strong converse for source coding with helper or broadcast channel. Alswede introduced a technique called ringing to prove strong converse for multiple access channel. So these are two classic techniques. And some of recent techniques include change of measure argument introduced by Gu and Efros. I'm going to explain this later. Recursive method and variational formula introduced by Ohama. Reverse hypercontractivity introduced by Liu and Verdu. Or edge removal method, or information stability, etc. So there are so many techniques. Today, in the first part of this talk, I'm going to present a general and simple recipe for proving strong converse, which we introduced last year. So in this recipe, there are two key ideas. The first key idea is change of measure argument introduced by Gu and Efros. And the second key idea is replacement of a hard constraint with soft constraint, which was introduced by Ohama. In the second part of the talk, I'm going to apply this recipe for parallel repetition theorem. Previously, a version of parallel repetition theorem was proved by using Dufinetti type decomposition argument, which is quite a difficult argument. And by using our recipe, we can provide an alternative proof for this claim using purely information theoretic method. So now let me explain what is change of measure argument. So we are given IID distribution PGN and a set C, such that the probability of this set is at least 1 minus epsilon. And when we prove strong converse, we would like to decrease error probability epsilon somehow. So one way to do that is blowing up the set C. So we blow up this set a little bit. Then the probability of blown up set become close to 1. This is one approach. Or alternatively, we can change the measure by conditioning on this set like this. So we condition on this set, then the probability of this set and the changed measure become 1. And interestingly, the divergence between the changed measure and the original IID measure is not too large. It's constant order. And in this change of measure argument, we first change the measure and we mimic weak converse argument to this changed measure. So this is change of measure argument. Next, let me explain what is soft constraint. So when we consider multi-terminal problems, we usually need to evaluate this kind of optimization problem for some bounded function g. For instance, the function g can be weighted difference of two entropy functions. And here, in this optimization problem, we have a Markov chain constraint in the sense that this auxiliary random variable u only depends on z1, not on z2. And usually, this kind of Markov chain constraint is a difficulty in multi-terminal problem. One way to avoid such a difficulty is to add penalty term describing the Markov chain constraint like this. So Markov chain can be also described by using conditional mutual information. So we add penalty describing the Markov chain constraint. Then we can take minimization over any test channel without any constraint. Then by taking the limit of the penalty, we can recover the original formula. Furthermore, we can also add penalty term describing the distribution. By adding this kind of penalty, then we can take minimization over any joint distribution. So we don't need to maintain the original given distribution anymore. And again, by taking the limit of penalty, we can recover the original formula. And this kind of penalized formula is quite useful when we consider change of measure argument. And as I said, in multi-terminal problem, proving Markov constraint, especially in single letter characterization argument, is the most difficult part. So introducing this kind of penalized formula has a lot of advantage. Okay, here let me explain three main steps of our recipe. So when we prove weak converse is completed if we can show this kind of super additivity, single letter characterization argument. In our approach, we first apply change of measure and we mimic weak converse argument for the changed measure. The second step is evaluation of some optimization problem for the changed measure. However, because the changed measure is not IID distribution anymore, so directly evaluating this optimization problem is not easy in general. So we add the penalty. As I said, the divergence between the changed measure and the original measure is not too large, so we add penalty like this. And then we prove super additivity of this penalized formula. Usually we can do this. And then apply variational formula, that is taking the limit of the penalty, and we recover a tight bound, tight strong converse bound. That is the flow of our recipe. And proving strong converse theorem boils down to two things. The first is identification of appropriate penalized function for each problem. And the second is proving superadditivity or subadditivity for the penalized function. Okay, so these two parts are difficult parts. Okay, so one application of our approach is Wyner-Ziv problem described in this figure. So we have xn and side information, and we reproduce xn with some distortion. So we consider, for additive distortion measure, we consider this kind of excess distortion probability. So detailed definition is not important, so Wyner-Ziv region can be characterized by like this formula using conditional mutual information and one auxiliary random variable satisfying this Markov constraint. And for technical reason, we consider this kind of weighted sum of rate and distortion. And when we prove strong converse, we introduce this kind of penalized formula by introducing penalties describing Markov constraint and also penalty describing the distribution. And then we first prove superadditivity of this penalized function. And then using this claim, we can easily show strong converse for the Wyner-Ziv problem. So in the case of Wyner-Ziv problem, we change the measure by conditioning on this kind of no excess distortion event and change measure and mimic weak converse, and then apply superadditivity of multilateral characterization, and we can get something like this. And finally, taking the limit of penalty, we can get strong converse. And proving superadditivity is a lot of manipulation. Most of them are elementary, but we have to find how to do this by trial and error. The key point is application of Chisal's identity. Okay, next I'd like to present an application of this recipe for parallel repetition theorem. So what is a parallel repetition theorem? So it is a claim about a two-prover game. So we consider this kind of game. So we have two provers and one verifier. And in this game, verifier sample some query x and y based on some distribution, and send the query x and y to the provers. And then provers reply u and v without any communication. Then if the query xy and the reply uv satisfy some condition, then provers win the game. In this kind of game, provers win means successful cheating. So the smaller winning probability is the better. Okay? And we can also play this kind of game n times repetitively. In n repetition game, first verifier samples n queries xn, yn based on IID distribution and send the query. Then provers send reply un and vn. Here, verifier's query is sampled according to IID distribution, but provers' reply may not be IID. They can use arbitrary strategy. And if every coordinate satisfies the condition, then provers win the game in this case. Furthermore, provers may access to some correlation to coordinate their strategy. For instance, they can access to common randomness or quantum entanglement or non-signaling box. And depending on what kind of correlation we can consider various kind of strategies. And this kind of game is an abstract model for multi-prover interactive proof studied in computer science or cryptography. And it is also an abstract model for Bell test experiment studied in quantum physics. And depending on what kind of correlation we consider, there are various kind of strategies. First, let me explain local strategy. So a strategy that is a channel from query xy to uv, reply uv, is called local strategy if it can be described as a convex combination of local deterministic function like this formula. This is equivalent to that u and v satisfy this long Markov chain constraint for some common randomness t. Then we can define the value of a single game by taking the maximum of the winning probability of the provers maximized over all local strategy. Similarly, we can define a value of the n repetition game by taking the winning probability of n repetition game maximized over n letter local strategy. And parallel repetition theorem is a claim about the behavior of this value for n repetition game. First, by using IID strategy, we can easily verify that the value of n repetition game is as large as the value of a single game to the power of n. Okay? However, this equality does not hold in general. There is some counterexample. And we'd like to know behavior of the value of n repetition game when the value of a single game is strictly smaller than 1. In 1998, Ratz proved the following. that is the value of n repetition game converges to 0 exponentially if the value of single game is strictly smaller than 1. So this is a quite simple statement, but it's very important statement in computer science, and proving this claim is quite difficult. Rat's proof is not that easy. Next, let me explain non-signaling strategy. A strategy is called non-signaling if these conditions are satisfied. That is, one prover's input, say y, does not affect the other prover's output, u. So it's a kind of causality condition, and it comes from physics assumption, physics requirement that no faster than right communication is allowed. And this is equivalent to that u and v satisfy these two short Markov chain constraints. For instance, measurement outcome from quantum entanglement satisfy this non-signaling condition. However, the set of all non-signaling strategies strictly broader than the set of strategies that can be attained by using entanglement. Actually, there is some known example called PR box. And for instance, in the case of Bell test experiment, the value of game with local strategy, the value of game with quantum entanglement, and value of the game with non-signaling strategy, all of them are strictly different. Okay, so now we introduce the value of the game for non-signaling strategy by taking the maximum of winning probability over all non-signaling strategies. And similarly, we introduce the value of the game, n repetition game with non-signaling strategies like this. Then Horenstein showed that for non-signaling strategies, the parallel repetition theorem also holds. That is, the value of n repetition game converges to 0 exponentially. Okay, so the study of parallel repetition theorem has a long history. As I said, Ratz first proved parallel repetition theorem, and his proof is a kind of difficult proof. Later, Horenstein provided a simpler proof of Ratz's result, as well as extension to non-signaling case. For quantum strategies, the general parallel repetition theorem is not known, and result known only for some special games. For multi-prover case, the prover with more than 2 provers, general parallel repetition theorem for local strategy is not known. But the parallel repetition theorem for non-signaling strategies is known. For instance, for full support game, non-signaling parallel repetition theorem was proved by Burman, Fair, Schaeffer. And an alternative proof was provided by using the Finetti decomposition argument by Friedman, Renner, Vidic. And for non-full support game, parallel repetition theorem does not hold in general. However, Rancière-Winter provided a kind of alternative version of parallel repetition theorem by introducing sub-non-signaling strategies. By using our recipe for proving strong converse, we can provide an alternative proof for Rancière-Winter's result. So in the rest of the talk, I would like to present a basic idea of this proof. But for simplicity of presentation, we consider 2-prover case. But our approach can be applied for multi-prover case as well. We consider a slightly modified version of parallel repetition. That is a threshold version of parallel repetition theorem introduced by Rao. So we consider this kind of value. Here, this NW is the number of winning by the provers. So we consider the probability such that the number of winning is larger than some threshold n delta. And we would like to prove this probability converges to 0 exponentially if the threshold delta is strictly larger than the value of single game. Okay. Here, by regarding this constraint as a kind of reverse of distortion, this claim kind of looks like exponential strong converse theorem. To prove this claim, we first introduced penalized value of the game like this. So we add a penalty describing non-signaling condition like this. And also we add penalty describing the joint distribution as well. Then we prove tensorization property of this penalized value. That is, the value for n letter game is n times the value for single letter game. Then we use change of measure argument by conditioning on the winning event. And by a similar manipulation at the proof of strong converse, we can prove parallel repetition theorem. Okay, so we introduced a simple and general recipe for proving strong converse, and in our approach we have two key ideas, and our approach can be used in various problems in network information theory, and it can be also used for parallel repetition theorem in computer science as well. In the case of non-signaling strategies, we have two short Markov chain constraint. And in this case, it is relatively easy to identify appropriate penalized function. But in the case of local strategy, we have this kind of long Markov chain constraint, and it's more challenging to find appropriate penalized function. And so one important message of the talk is information theory has some nice technique to reduce n-letter problem to one-letter problem. And sometimes that kind of technique is also useful in computer science problem as well. Okay, thank you very much.